Hello, welcome back. Okay, so our second concept is going to be discount rates. The discount rate R need not be on an annual basis. Now, most of the stuff that we do in this class will in fact focus on an APR, an annual discount rate, but to be clear, it need not be. So the important thing is to make sure that we're choosing the appropriate time horizon given the arrival of our cash flows. So suppose the annual interest rate is 12%. The quarterly interest rate, we're going to take that 12% and divide it by 4. The monthly, take the 12 and divide it by 12, so on and so forth. So annual cash flows must be discounted using the annual interest rate. A monthly cash flow must be discounted using the monthly interest rate, and so on and so forth. Okay. So make sure that the rate matches the correct time period. So we've got our time period, and we're going to divide that by whatever the number of compounding periods are per year. So if we have an interest rate of 8%, then we want to know the quarterly. What would that quarterly be? Well, for every single period, it's going to be 2%. If we had an interest rate of 8% per year, what would the daily compounding rate be? We're going to take our 8% and divide it by 365. So hopefully it's kind of clear that we always want to make sure that we choose the rate that matches the period. Okay, we're typically going to be working with annual cash flows and annual interest rates, but the discount rates, again, are almost always going to be quoted on an annual basis. However, on the occasion that you come across quarterly or monthly financial data, make sure you're using the appropriate discount rate. So let's do an example together. We've got our future value N, our present value multiplied by 1 plus R divided by M to the power of M times N. What does all that mean? I over nominal, that's whatever our annual percentage rate is, our nominal rate. So in the example we looked at, let's say it was 12. M would be the periods that we're looking at. So to keep it simple, if we have a 12% annual interest rate, but it compounds monthly, then we're going to take our 12, our 0.12, or 12%, and we're going to divide that by 12 to get the monthly interest rate. And what about our M times N? Let's say that it was going to be for 5 years. So now instead of us having this to the power of 5, we're going to take our 5 and multiply it by 12. Let's do an example so it feels a little bit less abstract. So what do we have? We have $100 at a 12% rate, semi-annual compounding for 5 years. We've got our present value, that's the 100, 1 plus R, but now we have to do our nominal divided by 2. Why? Because it's semi-annual. It's going to compound twice during the year. So that's 0.12 divided by 2. That's how we get our 0.06. What about our exponent? Well, it's semi-annual, so twice a year, and for how many years? For 5 years. 2 times 5 gets us our 10. Okay, we can also solve for the interest rate. So here we're going to kind of ask ourselves, what is it that we don't know? What interest rate would be needed to double your money at the end of 3 years? So what do I know? I know that at the future value, I want my current investment to be twice as large. So I know for every dollar I put in today, I'm going to leave with 2. Okay, so I know my future value and I know my present value. I also know how long I want to invest. I know my time horizon. In this example, we said it was going to be 3 years. Cool. The only thing that I don't know is my interest rate. I don't know the rate of interest that would be necessary in order for me to find that. So what do? I set up my present value, future value formula. I plug in my 2, my 1. I've got 1 plus X, my unknown, raised to the power of 3. I can then divide both sides by 1. So now I've got 2 equal to 1 multiplied by 1 plus I to the power of 3. If I take everything to the power of a third, what am I doing? I'm basically going to solve for I. So I take 2 to the power of a third, 1 plus I to the power of 3 taken to the power of 1/3. My exponents cancel on out. And now on my left-hand side, I've got a number. I've got the cube root of 2, which is a number, equals to 1 plus I, and I solve down for I. So in this example, we said it would require a 26% return, a 26% annual interest rate to double your money at the end of 3 years. Okay. Putting it all together, a firm is considering a project that will generate a quarterly cash flow of $3 million for the next 15 years. Suppose that the firm's annual cost of capital is 16%. What is the present value of the project's cash flows? So a few things. First, the project will generate a quarterly cash flow of $3 million. So this isn't an annual cash flow, it's a quarterly cash flow. We know the firm's annual cost of capital is 16%. So right off the bat, what do I want to do? I want to take that 16 and I want to divide it by 4. Why? Because I'm given an annual percentage rate, and what I want to do is make that quarterly. What am I going to do with my 15? I know it's going to be 15 years, but 15 years is really 60 quarters because every 1 year has 4 quarters. So I take my 15 years and I multiply it by 4. I throw my things into the formula and look what I find. Part B. Again, I do want you to make sure that you're working through these examples. Make sure that you can calculate these numbers. So it's not enough to see the formula. Set it up and solve it out. Take a moment, pause and solve it out and see where you're getting trouble. See where you're getting thrown off. If it's your order of operations or if it's missing a parentheses or whatever, just make sure you do it step by step. Part B. Suppose the cash flows are projected to grow by 1% per quarter. What is the present value now? So there are 2 things I want to point out. First, intuitively, if the cash flows grow, the present value should be larger. And you do observe that. The present value is considerably larger. Okay, that's fantastic. The second thing I want to point out, notice how we didn't take our 1% and divide it by 4 because it's already per quarter. It's already a quarterly growth rate, right? Okay, so we plug our numbers in. And again, hopefully this makes intuitive economic sense. As you set it up and solve it out, I want you to observe that it is a considerably higher present value for the same cash flows, but with a 1% quarterly growth rate. Okay, our third concept is net present value. And I know you've done net present value, NPV, so many times. What do we have? We've got our cash flow at time 0. So our net present value today, in today's dollars, whether or not we should take an investment. We've got our cash flow at time 0, which almost always is going to be negative because you almost always have to pay for an investment or pay for a project. Plus, we've got our expected cash flows for period 1, 2, 3, all the way up. And then each of those is discounted by 1 plus R, our discount rate. So this is kind of putting together the things that we've been building along as we talk about time value of money. One of the challenges will be in determining the correct discount rate R. That discount rate is going to reflect the riskiness of the project and so many of other things. So when we get into our next lecture, when we talk about market efficiency and when we talk about basically under what conditions can the firm be priced correctly, there we'll start to talk about the different things that are reflected in the discount rate. Another challenge is the numerator, calculating the expected cash flow in order to calculate the NPV. So let's kind of do an example together. Investments decisions in this course will typically be based on NPV. Now, I know you know this from your other corporate finance classes and from your other finance classes, but let's make sure we remember this. If the NPV of a project is greater than 0, then you should invest in the project. If the project has positive net present value, you should invest. If there is uncertainty in cash flows, meaning you don't know for certain what the cash flow for the project will be in year 2, year 3, etc., then you'll be taking the present value of expected cash inflows and expected cash outflows. You'll be taking an average, an expectation. So let's do that together. A firm is considering an investment that will generate cash flows for the next 2 years. These cash flows depend on whether market conditions are good or bad in each year. So you can see in year 1, if it's a good market, you get a cash flow of 20 million. If it's a bad market, you get a cash flow of 15 million. In year 2, if it's a good market, you get a cash flow of 30 million. If it's a bad market, you get a cash flow of negative 10 million. So right off the gate, we can see how the cash flows are moving up and down with the state of the economy. So when we get into discussing firm risk, we'll think of this as kind of risky cash flows, because when the market's up, the cash flows are high. When the market's down, the cash flows are low. Okay, what do we want to do? We want to calculate the expected cash flow in year 0, year 1, and year 2. We're going to assume that the project's cost of capital is 15% and that the project costs 15 million to undertake. Meaning, today, if we want to take this project on, we're going to have to spend 15 million. Tomorrow, cash flow 1, we're not certain. We're going to take an average. The day after tomorrow, year 2, we're still uncertain. We're going to take an average of that. So let's do it together. Okay, part A, if the project is undertaken, what are the expected cash flows in year 0, 1, and 2? Year 0, negative 15 million, because the project costs 15 million. What about year 1 and year 2? For year 1 and year 2, we're going to take an average. We know that both states of the world are equally likely. You're going to hear this language over and over and over. We're going to talk about states of the world. So in this example, we have 2 states of the world. We've got a good state and a bad state. We also know the probabilities. In this example, the 2 states are equally likely. But in the real world and in real life, we would have to assign different probabilities across these states. Okay, so they're equally likely, 50-50. So half the time it's going to be 20 million, half the time it's going to be negative 15. Cool. We take the average equals to 2.5 million. What about in year 2? In year 2, again, equally likely states of the world. If it's good, it's 30 million. If it's bad, it's negative 10. We take the average across those states of the world. So the last thing that I'll emphasize is that our expectation, it's again, an expectation, it's an average. So we still don't know what state of the world we're going to wake up in tomorrow or year 2, year 1 or year 2. So we're taking an average. Okay, part B, what is the NPV of this project? Should the project be undertaken? So what do we have? We've got minus 15 million plus 2.5 divided by 1.15. Where is that coming from? My 1 plus R. My discount rate was 15%. So I'm going to discount my expected future cash flow for year 1 by 1 plus R, 1.15, plus 10 divided by 1.15 to the power of 2. Same concept. 10M is my expected cash flow for year 2. 1.15, we agree, is my discount rate, and I'm raising it to the power of 2 because I'm looking 2 years into the future. When I sum up my cash flows at time 0, and the cash flows, my expected cash flows for years 1 and year 2, what do I find? I find a large negative NPV. The NPV is negative 5.26M. Should this project be undertaken? No. It most definitely should not be undertaken. If you have a negative NPV project, you should not take it. Because what you're saying is that you're going to spend more, 15 million, than you actually will recoup. The present value of what you're going to recoup is less than what you're spending today in order to go after it. So you're better off keeping the money in cash. Okay, our final concept is amortization. Amortization, it's a really long, big, fancy word. What it means for right now is basically paying back a loan bit by bit. How are we going to set this up? The punchline is that amortization, again, paying off something bit by bit, it's no different than an annuity. It's no different whatsoever. The only difference is when we calculate the annuity, typically I know what the cash flow is and I'm trying to solve for the present value. Here with amortization, it's going to be the opposite. I know what the value of the loan that I'm trying to pay off is, and I know how long I'm going to pay it off and the interest rate that I'm going to have to pay it off. What I'm trying to solve for with amortization is see that cash flow on an annual or periodic basis. How much do I have to pay off this loan? So let's do it. You take a loan for $1,000 with a 10% annual rate. You'll pay it back over 3 years with 3 equal payments. Step 1 is to set up a timeline. Step 2, we're going to solve for the payment. And then step 3, we're going to construct an amortization table. Basically, you're going to see how this thing is getting paid off bit by bit. So let's do it. Draw our timeline. Okay, at time 0, I've got a -1,000, right? That's the loan. At time 1, I got to make a payment. At time 2, I got to make a payment. At time 3, I got to make a payment. This looks really, really similar to an annuity. So what goes where? We can see that I've got my present value. That's the 1,000. This is how much we get today. C, that cash flow, how much we're going to pay each period, that's the payment. R, the interest rate, the discount rate is the interest rate on our loan, 10%. And then N, the number of periods of years of which we'll be paying this back will be 3. We'll be making 1 payment each year for the next 3 years. So let's plug it in and solve it out. What do we have? Our left-hand side, we've got 1,000 equal to C divided by 10% multiplied by 1 minus 1 divided by 1.1 to the power of 3, all of that in parentheses. Again, step by step, we always want to remember order of operations. So 1 divided by 1.1 to the power of 3, that whole thing equals 0.751. 1 minus 0.751 equals 0.249. Again, we're just going step by step. So if you're having trouble following, make sure that you're working along. Make sure that you can calculate each of these numbers step by step so that we're all on the same page. What do you find? What you'll find is that C equals to 402.11. So I'm going to make 3 payments of $400, a little bit over $400 to pay off this loan. And hopefully that makes intuitive sense. What you'll observe is that 3 times 402.11 is bigger than 1,000. And that makes sense. You're going to pay more to pay off the loan than you initially borrowed. Why? Because through time, interest is accruing on the loan. And that's evident here if we look at this chart. So what am I showing you? I'm showing you how each of these payments is paying off the loan. Your first payment, a considerable portion is going to interest, but the rest is going to the principal. And as you pay off the principal, there's going to be a smaller amount outstanding to compound. And the same is true for payments 2 and 3. So if that's kind of tough to see just based on the chart, the graph, let's kind of do it step by step. So year one, I'm going to have an interest payment of $100. So at the end of year 1, the balance on my loan will be the 1,000 that I borrowed plus the 100 in interest. So that first payment that I make at the end of year 1, that 402, 100 of that's going to interest, and then the rest is going to the balance, and the same with the next payment I make, and so on and so forth. So this is an amortization table. This is basically how you identify where your payments are going. Are my payments going to interest? Are my payments going to balance? And what's left back? So go with me step by step. Year one, beginning balance of 1,000. I have my first loan payment of 402. I also know that my interest on year one is going to be 101, or sorry, $100. So when I add everything together, the beginning balance is going to be 1,100. I'm going to pay 402. $100 of that goes to interest. 302, the remainder goes to the principal. Roll it on through, 698. I make my loan payment of 402. 698, I still have to pay interest. So I have an interest rate of 10%, gets about 70. 402, $70 of what I'm paying is going to interest. The rest is going to principal, and it's the same idea over and over. So we should be comfortable calculating the present value of cash flows. Even, meaning that it's the same cash flow, the same dollar amount, and also uneven. We should feel very comfortable discounting cash flows. We should be comfortable with the present value of an annuity, of a perpetuity, and of NPV. We should understand how to calculate NPV. And hopefully, we're more comfortable amortizing loans. Remember, it's no different than us taking an annuity. The only difference is that we know the present value and we're trying to solve for the C. How much are we going to be paying? We want to be careful to apply the appropriate discount rate to the appropriate time period. So if I have a quarterly, if I've got an annual rate, but I got quarterly compounding, I know I got to get this thing quarterly. If I got an annual rate and I've got monthly compounding, I got to get this thing monthly. Remember, the annuity and perpetuity are present value for payments that start next period, period T+1. Okay, what's next? Our next lecture will cover the role of financial managers and market efficiency. Where we're headed is going to be chapter 13 to discuss corporate governance and the role of the financial manager. And then also chapter 6 to discuss risk and returns. We're going to talk about what you do internally for the firm. And then we're going to look across firms, across many, many, many firms to look at our home market. And we'll use that when we think about risk and return. After establishing the role of the financial manager and the concept of market efficiency, we'll estimate the cost of capital and we're going to start to value firms. So again, the thing that I really want to make sure that we're all clear on is how to calculate our present value, how to apply our annuity formula, our perpetuity formula. We're going to use those formulas over and over so many times. So if there's any part of setting it up or any part of applying it that's giving you trouble, don't hesitate to ask a question in class. Don't hesitate to ask a question via email. Don't hesitate to use my office hours, and we'll make sure that everyone's on the same page because we're going to be using these tools throughout the course. So thank you.